I choose the name for all the work that I've been doing, quantum machine learning for image classification, embeddings, and loss functions. And well, this is the logo of this organization from Peru that introduced me to you all. So, well, since I already presented the fundamentals of this, all related to the quantum embeddings, to the PCA, the cross validations, and the algorithms thing, I'm just going to present some updates about this.
Seems like they have reshuffled the words in the
¿Ah? ¿Cómo?
They have reshuffled the words in the word value.
Well, first I will use this again because I really like it. How is the data embedded, encoded? Well, I will have classical data, and by using a quantum circuit, I would embed this data to the quantum circuit in order to classify it. And, well, in the case where I'm using only one qubit, the principal object of classification will be the Bloch sphere. And this state will be on the surface of the Bloch sphere, such that I can classify it using a quantum state discrimination context. And, well, for example, this is a 4-qubit quantum circuit, and this is just the ansatz of the embedding. For example, I don't know if there is like a pointer. As you can see, there will be a layer and a second layer, a third layer, and n layers that I will set for the circuit. And the entanglement designated for the circuit will be in this way. The first two wires of the circuit being entangled between each other, and using the second layer, I will introduce entanglement between the qubits left. I think that there was one thing left to explain the last time that I presented here, and was about the classical optimization part of the problem. And, for example, to improve the results that we got at the first time, Mikkel told me that there was some things that could be done. And, for example, a warm start. Let's say that I have a classical optimization context, and I will designate it between two limits, for example, for the weights and for the parameters. I think it could be useful to write here the loss functions and the weighted fidelity functions. For example, the loss function that we used the first time was this. And this is a common weighted fidelity function, where I will use only these two target states and the final states of the circuits that correspond to the embedding. But we try to use a weighted fidelity function that is in this way. It's written in this way. Let's say that I have this. I have three sums over this problem. And this f will correspond to a matrix where the fidelity functions are taken, well, this is just as this. This will be a reduced density matrix corresponding to each wire of the circuit. Let's say I will take the reduced matrix excluding this wire, the density matrix excluding this wire, and I will form a matrix corresponding to all the reduced density matrix of the circuit. And then I will train these parameters along with these trainable parameters. The problem of using this weighted fidelity function is that I will add more parameters to optimize in the problem. So, well, that is a problem that we have by the time that we were doing the code. And that is the reason why we introduced the warm start, the layer by layer optimization. Let's say that I have the last circuit that I show you, and I will optimize the first layer of the circuit, the second layer of the circuit, but the second layer of the circuit, I will use the already parameterized, already optimized parameters of the first layer. Adjusting the learning rate during optimization, let's say that this optimization can be stuck in local minima. So in order to get out of this local minima, the learning rate can be adjusted, so this local minima can be avoided, and saving the best parameters of the highest accuracy, this was done just, for example, if I have 10 iterations of the code, and I want to avoid that, for example, the last optimization has in the case where this last optimization has not so good results as the 2 layers before, I will stop the optimization problem. And for example, these target states can be obtained by, in the case, for example, for the 1-qubit classifier, can be obtained by these so-called maximally entangled states. And this is where the Thomson problem is introduced, because the problem to obtain these target states, for example, in the 1-qubit classifier, will be this problem, taking the maximum of the minimum of the distance of fidelity between 2 states, between a set of quantum states.
Maximum of minimum.
For example, let's say that this is a distance measurement of the states in the set that I'm working with. So I will take the maximum distance of, well, I will take the minimum distance between the quantum states that I'm working with. And then I will optimize this minimum distance in order to have the maximum distance that can be obtained in the case where I'm working with minimum distances.
So you're minimizing the fidelity, that's what it is, and then maximizing it.
Well, let's say that I have 3 points in the block sphere, and I want to optimize this problem setting this quantum state. And then if I will need 3 states, I will want to obtain 2 other states that has the maximum minimum distance between them. And for example, the configuration, the optimal configuration of that problem will be this triangle, equilateral triangle. But then what will happen when I will add more points to this problem? And the mathematical description of the problem is that it's essentially optimization problem for the minimum distance between 2 quantum states. And that is the so-called Thomson problem in case where I'm using physical context using charges in a sphere, or the Thomas problem that is a generalization of this problem in the case where I'm talking about packing of objects in a sphere or a geometrical figure. And this quantum state discrimination, I think that it's better to write it in the blackboard. Just an example of this. Well, let's say that I have these these states, and I want to distinguish between these states. The task will be related to the probability of making an error measuring these states. So, well, I think that I will. So, well, this probability is written in this way. For 2 states that are expressed by this. And, well, this operator will have eigenvalues that can give me some information about what I want to distinguish between the states. And let's say that I have this operator. Well, I will have eigenvalues in this way. Where these are the probabilities related to measuring one state or the other state. And well, this is just a start of the quantum state discrimination strategy, and I only did this trying to have a theoretical background of what is the circuit doing, because obviously I will classify using using classical optimization, but my question was always like, what is the theoretical background of this measurement problem? And well, this is all that I did these last weeks, and I expect you all to understand, or for me to speak well about this. And thanks you all, because I think I learned a lot. So.
Yeah, I have a question. In the last slide, in quantum state estimation, what you want is to be able to distinguish one state from a set, or every state.
I want to distinguish between the algorithm has to distinguish between the states that are designated to each data point that is being classified.
So then that formula is for two states.
Yeah, for two states only.
Example.
And yeah, that will be related to a object called Hailstrom bound that would bound the probabilities of measuring well or bad for the between only two pure states, because obviously we have not been working with mixed states since the embedding that we do will only plot the data on the surface of the block spheres. So, and well, this is related to the 1-qubit classifier, because working with, for example, a 2-qubit classifier would add more dimensions to the problem, and well, there is not a block sphere representation, a stacked block sphere representation for this, for that.
There is block sphere for the dimension D.
Yeah, but I think that, yeah, there is more.
And you can extend the hypothesis testing error to dimension. So, more questions? Comments? Okay, let's take the